So I have a little bit of leftover material. I realized I never talked about size of a group. So here is something that should have been probably done a while ago. A group G is said to have order n if it has n things in it. A group is after all a set with some operation, so it's a set. So if the set has 5 things in it, I say it's a group of order 5. And I write absolute G equal to n to say that G has order n. If G is infinite, we say that G has infinite order, and I write absolute G equals infinity. So Z has infinite order, Z mod 15 has 15 things in it, so it has order 15. The permutation group of n letters has order n factorial. S4 has 4 factorial, meaning 1 times 2 times 3 times 4, 24 elements, etc. Here's a little exercise that probably you should do. If G is a cyclic group with generator A, then the size of the group and the order of the group and the order of the element are the same. Remember, what is the order of the element? Order of the element means smallest natural number such that the nth power is identity. So what I'm saying is that if A has order 5, then what happens? You start with identity, take A square, A cube, A to the 4. These are all different. The first time you get back to identity, is 5. And after that, what happens? The 6th power would again be A to the 5 times A, which is identity times A, then A. So this is what a cyclic group of order 5 looks like, right? And then back to A. So if you keep multiplying by A, this is what happens, and this is the inverse. So this is already the group. So how many things does this group has? Well, 5 things. So that's all we are saying. And if the element A has infinite order, that means that all these things are distinct. If you keep taking power, it never comes back, and also in the other direction. So these are all distinct. So and then G is also infinite, because there are infinitely many things. Okay. Maybe we should talk a little bit about groups of small order. So group of order of G. Order 1. Well, there is only one group, of course, just the identity. It's the trivial group. Order 2, you know one group of order 2, Z mod 2. You could write down other things like plus minus 1. That's a subgroup of real numbers, multiplicative real numbers. Yeah, so 1 times 1 is 1, 1 times minus 1 is minus 1, and minus 1 times minus 1 is 1. That's the group law. So the inverse of 1 is 1, the inverse of minus 1 is minus 1. But this is not a new group, it's isomorphic to Z mod 2. To get an isomorphism, you just send identity to identity. The identity here is called 0, the identity here is called 1, and you send 1 to minus 1. And you can check that the addition here corresponds to the multiplication here. Okay, so order 2, there is only one group. Order 3, you still have only one group, actually, Z mod 3 up to isomorphism. In fact, we can prove pretty easily that if P is a prime odd number, then there is a unique group up to isomorphism of order P, which is Z mod P. So up to isomorphism, the prime orders are easiest to understand. There is a unique group of order P, namely Z mod P, where P is a prime number. This is actually an easy exercise from the previous one, actually, because if we take something in there, it will have to have some non-identity element, can show pretty easily that it has to have order P. In order 4, you first time see two different isomorphism types of groups. You have Z mod 2 cross Z mod 2, or you have Z mod 4. And I claim these are not isomorphic. That's because every element here has order 2, whereas this has order 1. Sorry, the identity has order 1, and the other three elements, these three, they all have order 2. Whereas this one contains a thing called 1, which has order 4. If you have an isomorphism from this a group to the other, something of order 4 here is going to give you a thing of order 4 on the left hand side. But there is nothing of order 4 on this side. 5 again is a prime, so you only have Z mod 5. 6 is the first time you see a non-abelian group. So 5, you only have Z mod 5. 6, you can write Z mod 6, which is abelian, and you can write, of course, S3, the permutations of 3 letters. That's also a group of order 6, and these are non-isomorphic because this one is abelian, this one is not. You could write potentially another one, Z mod 2 cross Z mod 3, but that actually happens to be isomorphic to Z mod 6. And this would be a fairly easy exercise to do this by hand. And these are not isomorphic since S3 is not abelian, whereas the other one is abelian. Order 7, you only have Z mod 7. Order 8, you have quite a few actually. Z mod 2 cross Z mod 2 cross Z mod 2. You have Z mod 2 cross Z mod 4. You have Z mod 8. And all these are non-isomorphic and abelian. You can verify that. And at least I can tell you one more non-abelian group. There is something called this group of quaternions. And this one, I can just sort of tell you by hand what the group law are. This one we didn't have occasion to introduce before. It has 8 things which I'll write as 1 minus 1, I minus I, j minus j, and k minus k. That's just the name for the 8 elements. And the minus sign is understood, so this will be the identity, and then minus I is minus 1 times I, etc. Same as I times minus 1, etc. And minus 1 times minus 1 is 1. So the minus 1 and the 1 have the usual property. The fun thing is how to multiply the ijk's. So I square, j square, k square, all are minus 1. It should remind you of square root of minus 1. That's why we use the notation I. And then ij is k, jk is I, ki is j. And you can check that these rules determine a multiplication table, and it forms a group on 8 elements called the group of quaternions. Order 9. You have Z mod 9 and Z mod 3 cross Z mod 3, and these are non-isomorphic, the same reason why these two are non-isomorphic, Z mod 2 cross Z mod 2 and Z mod 4. Order 10, you have Z mod 10. You could also write Z mod 2 cross Z mod 5, but that's actually isomorphic to Z mod 10. So there is only one. Order 11, 11 is a prime. Order 12, you have quite a few. You have Z mod 2 cross Z mod 6, Z mod 12. I probably wouldn't enumerate all of them either. Well, Z mod 2 cross Z mod 2 cross, wait a minute, you have also Z mod 4 cross Z mod 6, and then you have something called the even permutations of 4 letters. This is called A4. This is a group which we'll soon introduce. We haven't yet. And you also have, by the way, I missed some stuff, I realize. I missed the dihedral groups. You also have D6, the symmetries of the hexagon, which happens to be actually different from these guys. So yeah, at some point I think I stopped being exhaustive. So here, this one is same as the symmetries of a triangle. So this is same as D3. That was okay. But here you have another one, D4, which is different from all of these, the symmetries of the square. Couldn't forget, this is the group that we started with. So here we also have D5, symmetries of the pentagon. And these are non-isomorphic because, well, this one is non-abelian, this one is abelian. And it's a fun exercise to run this a while more. Like, very interesting numbers here are 60, 168, etc. So these are the numbers where really, really interesting groups appear. So I think I'll just stop at 12, because then things, after 24 or so, things get rather involved, and also it's sort of, if you don't have some system in place, then it's difficult to enumerate things. The abelian ones, we have a system to enumerate them systematically, but the non-abelian ones, it's a zoo, and it's a very difficult question how to get all of them. Okay, we'll start with the permutation groups next time.